Hello, my name is Ella Indseth, and I go to the Chesapeake Bay Governor's School Bowling Green campus. The purpose of this study was to determine if the macroalgae Chaetomorpholinum could be used to remediate coastal waters from the negative effects of the aquaculture industry. To do this, I set up an experiment to determine if C. linum had a significant impact on the phosphate and ammonia levels of fish-polluted water. I own a marine fish tank, and I have visually witnessed the effect that Chaetomorpholinum had on my tank, and this inspired me to create a study that would measure its impact on water quality and determine if it could potentially be used in the environment on a larger scale. Throughout this presentation, I will talk in depth about the purpose of the study, why I chose C. linum, I will give more details about C. linum, and then I will go over my hypotheses, methods, water collection process, experimental design, results, and I will conclude with a discussion of what I learned. The purpose of the study was to specifically test Chaetomorpholinum's capability of reducing phosphate and ammonia levels from nutrient-dense water. I wanted to use this data to determine the significance of Chaetomorpholinum on a larger scale, and I wanted to see if it would be a possible option to help remediate polluted waters from aquaculture farming. The image on the slide is an example of open net pen fish farming. This form of aquaculture farming negatively impacts the surrounding environment because it allows free exchange of water between the fish enclosure and the surrounding environment. The excess nutrients from the open net pen fish farming causes eutrophication, dead zones, and loss of wildlife in the surrounding environment. I chose to test Chaetomorpholinum's nutrient-removing capabilities because it is already used in the aquarium hobby. C. linum can also withstand a large range of salinities, and due to this I believe it has the potential to be used in multiple different environments. Like I said, I have personally witnessed C. linum's effects, and that is what initiated me to study this macroalgae. If you look to the side of the slide, there are two images of a hammer coral from my marine aquarium. In the top image, C. linum was present in the environment, and in the bottom image, it was not. You can visually tell that the coral is distressed in the bottom image due to its wilted polyps. If you look to the side of this slide, you'll see an image of C. linum. It has thick wiry filaments that are dark green in color. This specific type of algae will grow in mats across the seafloor or entangle roots of existing plants. It can be found in the Indo-Pacific, Western, Central Atlantic, and Mediterranean region. My alternative hypothesis with respect to the mean phosphate levels was that the phosphate levels of the control group, which was the tanks that did not receive the algae, would be greater than the phosphate levels of the experimental group, which was the tanks that did receive the algae. My null hypothesis with respect to the mean phosphate levels was that the phosphate levels of the control group would be equal to the phosphate levels of the experimental group. With respect to the mean ammonia levels, my alternative hypothesis was that the ammonia levels in the control tanks would be greater than the ammonia levels in the experimental tanks. My null hypothesis with respect to the mean ammonia level was that the ammonia levels in the control tanks would be equal to the ammonia levels in the experimental tanks. For this experiment, 8 fish tanks were set up with 1,500 milliliters of nutrient-dense saltwater. I rinsed the algae in clean salt water and spun it in a salad spinner to remove the excess water, and then I measured it and added 20 grams of macroalgae to 4 of the 8 tanks. My independent variable was the presence versus the absence of the macroalgae, and my dependent variable was the phosphate and ammonia levels of the water over time. The control group was the untreated tanks, and the sample size was n equals 4. The data was collected at the hours 0, 8.5, 24, 36, 48, and 70. To do this, I used a Hanna low-range phosphate spectrometer and an API ammonia test kit. At the conclusion of the data collection, a mixed design ANOVA with a between groups independent variable and a within groups repeated measures independent variable statistical test was used. My previous experience handling Chaetomorpholinum and the knowledge I have gained about it from other marine aquaria hobbyists was very helpful in the design of my experiment because I knew how to mimic the conditions it needed to thrive. I wanted to use nutrient-dense water to mimic the badly polluted waters that open net aquaculture causes when fish are densely corralled. To do this, I used baited minnow traps to capture killifish and left them in a 10-gallon bucket for 24 hours, and then they were released back into their original habitat unharmed. The salinity of the water was then raised to 35 parts per thousand using instant ocean reef salt. The images above show 2 buckets of water collected from the same source. The darker bucket was the nutrient-dense water that had killifish in it, and the lighter bucket was the untouched water from the same source. I had to repeat this experiment several times throughout the summer and fall months, and I actually found that the fish didn't produce as much ammonia in the fall as they did in the summer. This reduction in ammonia started to limit my measurements of Chaetomorpha's ability to decrease high levels of ammonia. To combat this issue, I actually found that I could use a heater to increase the fish activity and therefore increase the amount of waste that the fish expelled. The image on this slide is of my experimental design. This consisted of 8 individual fish tanks that sat inside of a separate plastic tub. The tub is filled with fresh water, and a heater and a circulation pump are placed inside to maintain a temperature of 26 degrees Celsius between all 8 tanks. I discovered this was the best way to heat the tanks because when I used an individual heater in each fish tank, there were inconsistencies between the temperatures of the tanks, and the tanks were just so small that they ran the risk of overheating and killing the algae. The 8 fish tanks alternate between control and the experimental groups. Each tank also has an aerator pump that prevents settling, and they were under a 100-watt LED grow light with a spectrum of 380 to 800 nanometers. This is the data table that represents the phosphate levels in each tank over the course of 70 hours. The red box highlights the mean phosphate levels of the experimental tanks that received the algae and the mean value of the control tanks that did not receive the algae. If you look at the data, you can see that the algae tanks decrease the phosphate levels over time and the no algae tanks increase the phosphate levels over time. As you can see, some of the data is represented by the value greater than 0.9. This is because the phosphate test that I used cannot read any value greater than 0.9. I chose to use this low-range test because it gave me a more precise reading compared to a normal phosphate test, but this factor did limit me from knowing how high the no algae tanks would actually get. In the future, I would like to use a phosphate test that can precisely read a wide range of phosphate levels. My ammonia data table shows the ammonia levels in each tank over the course of 70 hours. The red box highlights the mean ammonia levels in the experimental tanks that had the algae and the mean ammonia levels in the control tanks that did not have the algae. By looking at the data, you can see that the tanks that had the algae decreased the ammonia levels over time, and the tanks that did not have the algae had an ammonia level of greater than 8 over time. As you can see, some of the data is represented by greater than 8. This is because the ammonia test that I used only went up to 8 and could not read anything higher. I chose this ammonia test because it was fast compared to the other test, and I needed this because I wanted to be able to test all 8 tanks within the same hour. In future studies, I would like to find a fast test that could read a wider range of ammonia levels. This is a scatter plot that represents the phosphate data. The x-axis of the scatter plot is time in hours, and the y-axis is the phosphate levels in parts per million. The green line displays the tanks that received the algae, and the yellow line displays the tanks that did not receive the algae. My between group p-value for the phosphate levels comparing the tanks with algae and the tanks without algae was less than 0.001. Because of this, I can reject the null hypothesis with extremely high confidence that there is a difference between the algae and no algae tanks. I also created a bar graph to display the phosphate data. The x-axis is time in hours and the y-axis is the mean phosphate levels in parts per million. My sample size was n equals 4. The green bars represent the tanks with algae and the yellow bars represent the tanks without algae. By looking at the bar graph, you can also see that there is a decrease in phosphate levels of the algae tanks and an increase in phosphate levels of the no algae tanks over time. Here's the scatter plot that represents my ammonia data. The x-axis is time in hours and the y-axis is the ammonia levels in parts per million. My between group p-value for the ammonia levels comparing the tanks with algae and the tanks without algae was also less than 0.001. I can reject the null hypothesis with extremely high confidence that there is a difference between the algae and no algae tanks. Looking at the scatter plot, the line in the green represents the algae tanks and the line in yellow represents the no algae tanks. As you can see, the tanks that received the algae decreased in ammonia levels over time, and the tanks that did not receive algae stayed the same. The line of best fit was a polynomial with the order of 2 because it displayed the data the most accurately. Again, the value of 8 was the highest level that the ammonia test could read. Because of this, it is possible that the no algae tanks actually increased in ammonia levels, but it is unknown due to this limiting factor. Here's the bar graph that represents my ammonia data. The x-axis is time in hours and the y-axis is the ammonia levels in parts per million. The green bars are the algae tanks and the yellow bars are the no algae tanks. As you can see, the tanks that received the algae decreased over time and the tanks that did not receive the algae stayed at 8. The results of this study support that the implementation of Chaetomorpholinum in a marine environment would significantly improve the water quality by lowering ammonia and phosphate levels. If you look to the side of the slide, you'll see 2 buckets of water. The top bucket is a collection of the water from the tanks without algae, and the bottom bucket is the collection of water from the tanks that had the algae. You can visually see the difference in water quality between the 2 buckets. With this being said, theoretically, sea linum could be used to reduce the phosphate and ammonia levels caused by aquaculture open net pen fish farming. It is unknown the exact ratio of algae to water that is needed to be used to see a significant difference in the water quality. To implement this algae, a thorough investigation of its invasiveness and possible negative effects would have to be done along with a study to determine the ratio of algae needed. Not only did the study teach me about bioremediation and the dangers of the aquaculture industry, but it also taught me how to overcome obstacles and creatively use the resources around me to create a study and share it with others.